All right. Have you ever looked at a university exam question and thought, could I actually solve that? Well, today we're going to find out. We're jumping right into a real chemistry puzzle, and we're going to crack it together. Let's get started.
So, here's our target. This is question 5, straight from the source. What we've got are two mystery graphs, graph A and graph B. They're both charting some property for the elements in the third period of the periodic table. You know, from sodium all the way over to argon. The thing is, one of them shows atomic size, and the other shows ionization energy. That's the energy it takes to rip off an electron. And our job? Figure out which is which.
Okay, so a university chemistry puzzle. To solve this case, we need to gather some clues. We can't just wing it, right? We've got to really dig into the science behind what's happening. So let's start our investigation.
First up, clue number 1, atomic size. We're going to investigate how big an atom really is. You hear chemists talk about atomic size all the time, but what does that actually mean? Well, it all comes down to something called the atomic radius.
So what is atomic radius? Think of an atom like a tiny, fuzzy cloud. At the very center, you've got the nucleus. All around it, you have the electrons buzzing around. The atomic radius is basically just the distance from that center nucleus out to the edge of that electron cloud. Simple enough.
So what decides how big that fuzzy cloud is? It really boils down to one simple idea. Opposites attract. The nucleus is positive, the electrons are negative. This means the nucleus acts like a powerful little magnet, constantly pulling those electrons in closer. And here's the key. The more protons you pack into that nucleus, the stronger that magnet gets. So let's think about this. As we move from left to right across that third period, sodium, then magnesium, then aluminum, we're adding one proton every single time. So if that magnet in the middle is getting stronger and stronger, what do you think happens to the overall size of the atom?
This is where it gets a little weird, kind of counterintuitive. You'd think adding more stuff would make the atom bigger, right? Nope, the stronger magnet wins. The atoms actually get smaller as you move across a period. That extra pull from the protons yanks the electron shells in tighter and tighter. And boom, that is our first major clue. Atomic size goes down as you go across a period.
All right, clue number 2, ionization energy. Now this sounds way more complicated than it actually is. Think of it like this. It's the price an atom has to pay to lose an electron. It's all about how much energy you have to put in to steal one. To be specific, first ionization energy is the energy it takes to remove the most loosely held electron, the one on the very outside of that fuzzy cloud. Really, you can just think of it as a measurement of how tightly an atom is holding on to its electrons. And this is where it all clicks together. See, this connects right back to our first clue about size. Remember how smaller atoms have their electrons pulled in tighter by that stronger nucleus magnet? Well, if those electrons are closer to the nucleus, the pull is way stronger. They're being held onto much more tightly, which means it's going to be a lot harder to steal one.
Okay, let's put 2 and 2 together. We know the atoms are getting smaller and smaller as we move across the period, and we know that smaller atoms hold their electrons tighter. So, what does that mean for the energy you need to pull one of them off? Is it going to take more energy or less?
You got it. It gets way more difficult. You have to pump in more and more energy to fight against that stronger pull from the nucleus. So our second big trend is clear. First, ionization energy generally increases across a period. And with that, I think we have everything we need.
All right, it's time. We've done the legwork, we've got our clues. Let's head back to the original mystery and apply what we've learned to the evidence. It's time to solve these graphs.
Okay, let's compare our trends to the graphs. Clue number 1, atomic radius. We figured out it should decrease across the period. Which graph shows a downward trend? That's right, graph A. It's a perfect match. Now, clue number 2, ionization energy. We predicted it should increase. And look at that, graph B trends upwards. It's an open and shut case.
And just like that, we've solved it. Graph A, the one going down, has to be atomic radius, and graph B, the one going up, is first ionization energy. Case solved. But, hang on a second.
But hold on. The best mysteries always have a twist, right? If you look really close at graph B, the ionization energy one, it's not a perfectly smooth line going up. There are these little blips, these dips in the line. And like any good detective knows, you can't just ignore the weird details. That's usually where the really interesting stuff is hiding.
So why is it suddenly easier to remove an electron from aluminum than from magnesium? Check this out. The energy goes up from sodium to magnesium just like we predicted, but then it takes a nosedive for aluminum. That doesn't fit our rule. It should be harder to take an electron from aluminum, not easier. So what on earth is going on here?
The secret here is all about electron configurations, how those electrons are actually arranged. See, magnesium's outer electrons are in what's called a 3s subshell, and it's completely full. 2 electrons perfectly paired up. It's super stable, very happy. Aluminum, on the other hand, has that same full subshell, but it also has 1 extra lonely electron sitting by itself in a higher energy 3p subshell. And it is way, way easier to just pluck off that 1 lonely electron than it is to break up magnesium's super stable pair. That's the verdict. So that's why we see the dip.
And here we go again. If you look a little further down the line, the same thing happens. It climbs up to phosphorus, and then bam, another dip for sulfur. Why the drop from phosphorus to sulfur? It's the same kind of pattern, so there must be a similar reason behind it.
You guessed it, it's another case of special stability. This time it's about a half-full subshell. See, the p subshell has 3 little slots, or orbitals, and phosphorus has exactly 1 electron in each of those slots. It's perfectly balanced, and that makes it surprisingly stable. But then sulfur comes along and adds a 4th electron. Now one of those slots has 2 electrons paired up, and since electrons are both negative, they push each other away. That repulsion makes it easier to just kick one of them out. So it's actually harder to break up phosphorus's stable setup than it is to remove that repulsed electron from sulfur. Pretty cool, huh?
Okay, so now for the final verdict. We've solved the main mystery, we've explained the weird exceptions, now let's look at the grand finale of this whole trend, the case of the noble gas, argon.
So why is argon the grand finale? Well, it's the perfect bookend for both of our trends. First, size. It's got the most protons in the period, which means it has the strongest magnetic pull, making it the smallest atom of the bunch. Second, energy. Its outer shell of electrons is completely, perfectly full. That is the most stable an atom can possibly be. So trying to remove an electron from argon, it's going to take a huge amount of energy. It's the peak of our graph for a very good reason.
You know, when you step back, this whole exercise shows you something amazing. The periodic table isn't just a list of elements. It's a predictive map of their chemical behavior. Once you know the rules of the road, you can predict what's going to happen. It's incredibly powerful.
So, there you have it. We just took on a university-level chemistry question and cracked it, just by understanding the patterns baked right into the periodic table. It makes you think, doesn't it? With so much order built into its design, what other secrets is the table hiding in plain sight?